Okay, we are going to continue our discussion of parallel transport. Not because we haven't done it enough, we probably have done it enough, but because I'm not finished. I think there's a lot more to look at. I'd like to do the whole idea of parallel transport in CFREE notation, because I'd like to have everybody develop a facility between converting between CFREE and comp notation. I think that's an important skill to master for this understanding and learning and reading different books. Plus, doing it just gives us another swing at understanding the concept of parallel transport, so there's really no harm in doing it again. We're not on a clock here, right? This is not a semester course where there's tests and there's a completion date. So going through the same material different ways, that's not a problem to me. Anyway, so let's begin. I want to point out a little bit of interesting thing about, of course, notation. We always have a curve when we're talking about parallel transport. We have a curve, and we have a point on that curve, and in that point on that curve, we have a tangent space. And that tangent space is a vector, complete vector space, and the basis of that tangent space in the coordinate basis would always be written as these partial derivatives. If it was the cotangent space, it would be the basis vectors would be in the coordinate basis would be these one forms. But we're not dealing with the cotangent space right now. It's just the tangent space. And all the vectors can be expressed as some in the component notation as x mu partial mu. In the CFREE notation, we don't bother with that, and we just call all of the vectors inside this tangent space. We just give them their name, and if it was in print, it'd be in boldface. But I might throw a vector symbol on top just because I have trouble with boldface on this whiteboard. And if I just pick one point on this curve, and if the curve is parameterized by tau, and maybe I start tau at 0 and just go up to some higher values. There really is no limit to tau. It can go in. 0 is just an arbitrary spot, right? And if I said that tau, and then the curve, I have to give the curve a name. And the curve's name is gamma. So gamma of tau is the map from R to S. And this point here that we're dealing with, this point right here, that's going to be tau, or a gamma of tau equals 0. Gamma of 0. And all I have is a vector sitting in that tangent space. I've identified some vector there. And my question is, if I went to some other point, say gamma of some value, say t, at that point, this point has its own tangent space, right? This is the tangent space of gamma of t, whereas this is the tangent space gamma of 0 of s. And my question now is, what vector here living in this tangent space is parallel to x? So there's some vector in here that is parallel to this vector, but lives over here. And notice I'm not talking about vector field right now. I'm saying I picked one vector at a point, and I'm asking for its parallel counterpart at some other point. And the reason I don't need a vector field to talk about that is parallelism we now know is defined by the metric. So presumably our space S is S, I'm sorry, not the metric, a connection, S and a connection. We haven't introduced the metric yet. There's no metric here at all. So, but the connection is all I need to know to parallel transport a vector from this point to this point. I don't need the metric. Eventually we'll talk about, and as I've mentioned before, the metric defines a connection that will do just fine to determine parallelism, and that is the foundation of how it's used in general relativity. But in the meantime, until we have a metric, as long as we have a connection on the space-time of some sort, we can execute this parallel transport. So you can imagine doing this for all these different values of t. You know, t starts at 0, and t moves all the way up to unlimited values. This point, gamma t, moves along this curve. At every single one of those points, every single place, you're going to have some vector that's parallel to x. Now, the question is how do we symbolize? One question is how do we symbolize that vector at all of these different places? And what we'll suggest is that, well, we know how to find this vector. We know about the parallel transport equation. So we know that the vector at all of these different spots is going to satisfy, well, if we solved the parallel transport equation, right? If we solve this expression, if we solved dx d tau plus these connection coefficients, alpha, beta, sigma, x, beta, this has to be an alpha, times d gamma sigma d tau equals 0. If we solve that, we are going to end up with x alpha as a function of tau. Right? The solution of these four differential equations that are coupled together will give us x alpha as a function of tau. And what's nice is that this will be auto parallel on gamma. That means I put in tau and I get the vector that is parallel to some initial condition. So I have to solve this with the initial condition of x and at gamma of 0. That's my initial condition. That's this value right here. And once I've put in that initial condition, the vector field I get as an answer to this expression, to this equations, to these differential equations, that vector field will be autoparallel. And therefore, this will now be x of, say, if this is x of t, why don't I call this one x of s, if that's gamma of s, and then this is gamma of r, say, and then this would be x of r, and then this would finally be x of t. And that would be an autoparallel field. And of course, we have to use the comp notation to develop the differential equation to actually do the solution, right? But in the meantime, if we want to stay in the CFREE notation, we presume that this is possible, and we just define this autoparallel field, x of tau, and we say that this is x of 0, x s, x r, and x t, and they're all parallel to one another because we've derived this expression for x from the parallel transport equation. So with this notation in hand, we are going to generate an expression for the parallel transport equation using the comp notation from the beginning. And the way we do this is we're going to introduce an operator, omega. It's got an awful big feet on that omega. Omega, and we'll call this omega operator omega t comma s. And omega is an operator that's, and all operators have to be defined as mappings, and it can be a mapping from the tangent space at gamma of s to the tangent space, I guess I need an s there, of t. And at first this seems kind of ridiculous, but the way the operator works is ts, it's not a tau now, that's a t, ts operating on x of s will equal x of t. So remember that x of tau, of the variable tau, is a autoparallel field, or a vector field that is autoparallel on the curve gamma. So it's only really defined on gamma, and gamma is a curve that is parameterized by tau. Notice, by the way, that you can name these curves in a lot of different ways. Well, in at least two different ways that we're dealing with here. Tau is the parameter for the curve, and the name of the curve is gamma, because gamma is the map that takes tau, which is a real number, and gives you a curve in S. So you can name the curve after gamma, but it's not like tau is the parameter for other curves, right? It's not like there's another phi of tau, and you have to figure out which curve you're going to. Tau, each curve is going to have its own parameter. And because of that, tau could name the curve too. Tau could easily be the name of the curve. So saying x of gamma of tau is redundant, because tau and gamma both really identify the curve. So you can make the mapping gamma kind of implicit and just say x of tau, understanding that tau is the parameter for some curve, and that curve may even have a name, gamma. But I've seen some treatments that just leave the name out altogether. So, but what we've done is, it seems almost silly. It's like we've made a complicated version of x of t. But this operator is the parallel transport operator. When applied to x of s, it will give you x of t, where we understand that we're really talking about x of tau is the function we're talking about, which is really a vector field along a curve tau. Right? So this is all sort of introducing certain forms of shorthand. Now within this notation, we have a way of expressing the parallel transport equation. The parallel transport equation, it was always given this, split by this, gamma dot of, let's say I'm going to go with y here. I'm going to go with y. I'm changing from x to y, just because I'm writing the equation in generality. That thing here is supposed to equal 0, right? That's the parallel transport equation. In our new notation, the way we're going to understand that is the derivative with respect to s of omega ts, this is evaluated at s equals t, of gamma of s. And that thing has to equal 0. And so this is the parallel transport equation in the abstract notation that utilizes this method of parallel transport, right? So trying to understand what this is the derivative with respect to s. Well, s is, this is an auto parallel field, and s is the parameter value that defines the place on the curve. So of course this could be y of gamma of s, right? And this operator, it's also, the operator itself is a function of s, right? Because you have to choose s and t. So this is the rate of change of this object as s with respect to s, and it's evaluated when s actually equals t, which is the identity, by the way, right? Because gamma, omega of tt is going to be the identity. In fact, there's a couple things. Omega of tt equals the identity operator, and also omega of ts, omega of s to t to r is omega of s to r, right? There's that transitiveness. And that's because along this curve, I think back here, along this curve, it's unique, right? There's only one parallel vector to this initial vector at this point. And if you parallel transport that to here, there's only one parallel vector that's going to be parallel to this one. So to go from here to here to here, it's got to be you've got to go through the same batch of parallel vectors. It's because the differential equation has a unique solution, and because of that, that ultimately translates into this statement here, that the operator from s to t followed by the operator from t to r is the operator from S to R. And these are, by the way, are finite distances, where finite means they're finite values of the parameter tau, right? So tau, this isn't an infinitesimal distance like we've talked about previously. These are finite distances of tau. And the word distance is a little awkward because we don't have a metric. So what I should say is finite changes in the value of the real number tau, which parameterizes the curve. In some sense, we do have a metric, right? If you have a curve and tau is a parameter on the curve, you know, in some sense, tau is a bit of a metric. It does define the distance along the curve in terms of some parameter tau. The problem is you can easily reparameterize tau without any trouble. That would be similar to just changing the scale of the curve or something like that. But this expression falls back from the uniqueness of the solution of this differential equation. So now I want to show why this expression and this expression are the same. And to do that, we're going to start, we've got to remind ourselves, let's remind ourselves that gamma of t is omega drag from s to t of y of s. I said gamma, but I meant y of t. So the vector, the autoparallel vector at t is the autoparallel vector field at s run through this operator. Well, we can think of this in terms of components. And, you know, typically to prove these things for our CFREE notation, we always dive into component notation to do it. But this vector, y of t, has components. So let's think about the different components. Well, that would be the components of this guy, right, because they're the same. And then you've got to look at this and realize, okay, y of t is a vector, right? So this vector can be y alpha partial alpha. And this guy here, it's also a vector. And each of these components here is some kind of collection of these components there. So this can be understood as omega operating as a matrix. You can think of omega from S to T. It's going to have a new component, sigma y sigma. And so if I erase this expression here is sort of the full component version of this expression here. I guess I have to include that in front on this side. And what you can see is that this is just a dummy summation over the components of y at s. Each of the components of y at s is going to contribute somehow to the new component of the autoparallel version at t, and that amount of change is going to be all wrapped up and expressed in the components of this somewhat mysterious operator that moves y of s to t. Now, when I say it's a mysterious operator, remember, we're just talking about we know it exists because we can solve for this field, right? The nature of that operator is simply, okay, tell me where we start, tell me where we end. I'll solve this equation and evaluate it at. I'll solve this equation, use the initial condition of where we start, and plug in the value of the parameter for where we end, and I'll change those vector components into those. So it's not a mysterious operator, it's really describing that process. And it turns out that that process, these are going to be functions. To do this, these are all going to be complex functions of s and t. And in particular, since it's a function of s, taking its derivative with respect to s, we're going to ultimately see that is going to define the equation for parallel transport. So we have this expression for the components of y of t. And just to be completely clear about it, we can write it down like this. We can say omega ts y of s. Right, notice this s has to always match that s, right? Because this guy here is taking a vector from s to t, right, in that direction, from s to t. So it has to start at s, right? It has to have an object that starts at s. So if I write that, and I say what I want to know what the second component is, right? The second component, well, that's going to simply be omega ts second component 1 y1 of s plus omega ts second component, I guess 0 component, 1 component. Since we're doing general relativity, I'll stick with 4 dimensions starting with 0 plus omega ts 2 at s plus omega ts y3, I guess this is omega 2, 3 y3 of s, right? So that's it blown up in its explicit form. All right, so now we know that y of t satisfies the parallel transport equation. So we know that that satisfies dy mu dt plus alpha beta d gamma alpha t dt times, let's see, y beta equals 0. And remember, when we write down y beta, we're thinking y beta, it's a function of t in this case. I'm using, I write tau there, but what I mean is t, because I'm talking about this guy here, right? I'm still using y of t and y of s. So sometimes my t's are beginning to look a little like taus. When I write a tau, I like to do a curly top like this in a straight line. When I do a t, I tend to do that. So understand, that's a tau and that's a t, and these are all t's. Okay. So this, and I'll just as a reminder, whenever you look at a differential equation in this stuff, understand, what are you solving for? Here we are solving for, and you can tell by this term, you're solving for a function of y as a function of t, and it's going to solve this whole differential equation, and this is a known quantity because we presume that we know the path, right? We know this function, we know what path we're interested in moving along and finding the parallel transport along. And this connection is part of the space-time. It's a given piece of the space-time, right? We have a connection. Now right now I've converted everything back into comp notation, right? It's just this thing we do when we do these proofs. It's sometimes easier to do the proofs in comp notation. And right now I'm trying to prove that this expression here is equivalent to this expression here. And I'm going to do it through stepping through comp notation. So, but probably what I should do is make explicit the t here. So I'm making those t's explicit. So now I did it here, by the way. I could have just left the gamma without the t. Right? That wouldn't have. I mean, you know that gamma has to be a function of t if you have d gamma dt. If that wasn't there, you would still know that gamma was a function of t. So there's a certain amount of redundancy here. So it's a battle between heavy, thick notation and super duper clarity, right? So we'll go for super duper clarity right now. So I can rewrite this expression as d of omega ts gamma s, and I'll use that summation notation that we had before, and this will be, say, mu, and this is at s, right? And oops, this not in here, sorry. It should look like this. Sigma, mu, gamma, sigma of s. I've now changed it to a function of s, and then this is still dt, because this whole expression here, well, that equals y of t, right? And then this is plus, by the way, this is also a function of space-time here. So this would be a function of t too, right? It's just, but it's not, there's no derivatives being taken, right? That is, the connection coefficients are a function, change along the curve, right? So they're also a function of so everything's a function along this curve, right? And then this guy is gamma, mu, alpha, beta. Then it's still d gamma alpha of t d t. And then we make the same substitution here. Omega t s, and it's sigma beta gamma sigma of s. And this thing equals 0. And then what we note is we note that we have gamma s here, gamma s here, and therefore we can pull it out, and the fact that it's gamma s is arbitrary will allow us to make this 0. So I'll do that out in full form. It's like this: ts mu sigma dt plus gamma mu alpha beta d gamma alpha dt. I'll get simpler as we go on, right? So I'll start dropping the obvious dependence on t. B sigma. Now this whole thing is with y sigma of s, and it equals 0. So the idea, the reason you can get rid of this is because this is arbitrary, right? We're allowed to have any vector field to start with, or we're allowed to there's no conditions on this. So in order for this whole thing to equal 0, if one factor could literally be anything, the only way that could always be true is if this thing here was always 0. So that's why we allow ourselves to then get rid of that and just write the expression this way, right? And once we've done that, we can also, right, that's now our expression, that equals 0. And I've done all that just for that last line where I can write d gamma ts mu sigma dt equals minus this connection coefficient d. Well, why don't I just go real crazy, right, and just say gamma dot, right? Omega ts beta sigma. Right, so that's the statement I wanted to demonstrate. And here, of course, I'm using gamma. I'm using this for this. And the dot obviously means the derivative with respect to something. Well, there's only one possible thing you can take it with respect to. It's t. So if you know the parameter, and we know that t is the independent variable from the left-hand side, so it's there. It's all clear. You just have to fight for it a little bit sometimes. I guess that means it's not clear if you have to fight for it, but it does make the notation cleaner and cleaner. In fact, I probably could have put a dot over this and gotten rid of the d by dt if we knew about t very well. So anyway, so this expression is, we're already at something that's beginning to look like what we want to show, right? We want to show this, right? And I already have something now that expresses a derivative with respect to one of these subscripted variables I have an expression for that now in terms of the object itself, the connection coefficients, and the derivative of the curve. Right, so that's very useful. And I can go even further if I evaluate this thing at t equals s, at t equals s. If I do that, I end up with an expression that looks like this. The right-hand side ends up being minus gamma mu alpha beta. Better go back to d gamma of t, d t, and then this thing becomes omega ss beta sigma, but omega ss beta sigma, that's the identity function, right? So that has got to be delta beta sigma, right? For that matrix element to be part of the matrix, to the identity matrix, it's going to have to be a delta function. So that delta function will allow me to collapse the betas into the sigmas, and I will end up with minus gamma mu alpha sigma d gamma alpha, there should be an alpha there, dt. And this is the derivative of ts mu sigma dt evaluated at s equals t. And that expression, that's a negative sign. That expression is sort of the final answer when you evaluate this guy at s equals t, which is what we are going to do, right? Eventually, that's part of our ultimate goal. So we've kind of gotten this in place, ready to go, make the next substitution. And so now we just can write down the whole thing. And we would write it the following way. We will write d by ds of omega ts of y of s mu evaluated at s equals t. That's the definition we're trying to prove. We're trying to show that this object here is our the left-hand side of the parallel transport equation. And I'm going to just turn it into that using everything we've just learned, right? So the way I'll do that is I'll go d, it's actually kind of tricky, d by ds, then I will go to the inverse, and I'm going to swap the subscripts, st of y of s mu evaluated s equals t. So this is the same as this, because when I switch from s to t, it's the same as taking the inverse. So if I switch from s to t and then take the inverse, this guy is exactly the same as that guy. Right? So I've just done this little notational switch. And this can stay at s because I'm dealing with the inverse of this thing. So switching these two indices and making is the same as inverting. So if I switch them and invert them, I've done nothing. So I've effectively left it alone. So then I will write that equals, and then I'll use the chain rule, d by ds, and this will be omega inverse st, and then it's mu beta, and then it's y of s beta, and this is evaluated at s equals t. So I'm doing the chain rule here on this, plus omega st inverse of d ds y s of mu, at s equals t. Evaluate. So that's a simple, I'm sorry, did I say chain rule? I meant product rule. It's the product rule applied to this expression right here. And then I make the one little tricky maneuver. That is, I take this guy and I replace it with minus d by ds of omega st, omega st mu beta y beta at s equals t. And I'll show you why we can do that in a moment. Plus, and then on this side, I don't actually, on this side, I'll go ahead and evaluate s equals t. At s equals t, this becomes this becomes the identity operator, so this just becomes d ds y s mu. Right, so I've evaluated the s equals t for this part. But let's have a look over here at the change from omega inverse st to losing the inverse and just putting a negative sign up there. Let's see if we can understand that. All right, so to understand that, let's see if we can break it down. I'm going to break it down to a little segment of our curve. This is the point represented by the parameter value s, and this is the point represented by the parameter value t. And this is the autoparallel field at s. I'll do that in black. And then this is the autoparallel field at t, and I'll do that in red. And we know that y of t equals, say, omega ts y of s. So when we look at this expression here, let me write that down again over here. It will be d by ds of omega st inverse of y. And we actually broke this down into component form, right? So we have this expression. So our question is, how do we interpret this expression, right? Well, this guy in here, so first of all, I guess what's important to understand is that there's some parentheses here, right? It's really this thing. I better erase this y here. Y beta, right? Because it came from, we developed it from a product rule. So it's this first derivative part. So now this is the a change. It's a vector change, right? These are the components of a vector at s, right? So you would have the vector at s, the operator that goes from s to t, and then the vector at t. Here you have the vector at s, and this is an operator that goes from s to t because it's the inverse of an operator that goes from t to s. So this thing here is going to ultimately represent the change in the vector components of what the components were of y at s to what the new parallel components will be at t. So if we just move the components of s over here, we might get something that would look like that, say. And that would this vector here sitting at t has the exact same components at s, which would be what parallel transport was in the absence of any connection, right? If the connection was 0 and it was flat space, you would just take the components here and move them here and call it parallel. But that's not the reality. If I did that and moved it here, I would get this vector. But the real parallel vector is this one, which has been moved or shifted, its components are different because of the connection. And that difference is this vector right here, the vector between what it would have been had it been flat space and what it is because it's curved space, right? And that's kind of what this thing is telling us. This thing is part of that change. It is where the other part is, of course, omega st inverse mu beta d by ds of y beta of s, right? So this is part of that, of what that change is. Now, but the point is now, if we took the same logic and we took yt and just put its components in s, we would end up with something like this, which is not the parallel transport of yt to s. What that would be, the parallel of yt to s should be this guy, y of s, by the way we've constructed everything. So the difference there is this vector here. But you can see these two things will have to be opposite of each other, right? If I do the inverse parallel transport here, this vector, which corrects for the non-flatness, is going to just be the opposite of if I did the parallel transport here. So that's what allows me to eliminate this inverse by just changing the sign of all of these little vector components. And now I've already written down the next step after we take this guy here, and we are going to now substitute in for this expression based on what we learned here, right? That the derivative of omega ts with respect to t is evaluated at s equals t is these connection coefficients times the derivative of the curve itself. So I can make this substitution right here. And that comes from that prior work we did, and then of course the yb comes down, and then I evaluate it at s equals t, and then add this term into it, and I get this term, right? And then when I look at this plus this, I see the familiar expression, which I guess I'll do in black. If I reorganize it, I would get dy mu ds plus gamma mu alpha beta d ds gamma alpha, where gamma is a function of s, y beta s. But that we know is the comp form of this expression. And then ultimately that is what we were trying to show. We were trying to show that d by ds of omega st, let's see if I can find the exact thing, omega ts gamma s, oops, omega, let's see, ts y of s mu at s equals t. So that's what we wanted to show. And we did. We started up there in the far corner here with this expression, and we worked our way through it, and we ended up with this expression down here. So now we have, using the operator notation, we have a way of writing the parallel transport equation, which is this. And that's a worthy goal for one lesson, just to see yet a different form of notational architecture at work, this operator notation. And you should be comfortable, relatively comfortable moving between them, but the one you really need to be comfortable with by and large to really get at the introductory and intermediate GR is, of course, the comp notation. This stuff here is really important, and from time to time I've seen older books do proofs in this form, but it really is all the same. It's all the same mathematics. I don't want to say it's just a matter of notation, because the insights from here to here, they're very different. This is very computational, and we actually do a lot of proofs. You even saw, in order to make a proof about this abstract notation, we immediately went into components. So, you know, it's very tempting to just turn everything into components, work with components, and then sort of turn them back, because we know this definition from our previous work. So now we know this definition from this work today. All right, so the next lesson, what we'll talk about is, we'll talk a little bit about parallelism of general tensors, right? There's a nice abstract proof of how to define parallelism for general tensors, and we'll use both of these notational systems to do that. And then we'll see how that links up with the definition of covariant derivatives for tensors of arbitrary rank. And from there we will, let's see, I'm kind of looking at my notes here. Then we'll go into defining an abstract approach of defining the directional or partial derivative, and then that will lead us into the notion of the metric connection, where we are basically claiming that parallel transport should not change the inner product between vectors. So if I take two vectors in one tangent space and find the metric between them, or if I compare them using the metric, then I should be able to parallel transport those two vectors to any other point and compare it with the metric there, and I should get the same answer. And that's what ties the metric to the connection. Okay, so we'll see you next time. Oops, before I go, I just noticed one little thing here at the end. I left that mu there, which is still in comp form. The ultimate expression of this is d by ds omega ts y of s evaluated at s equals t equals 0. We get rid of that final comp. I mean, once we express this in the abstract vector form, we don't need those components. Component-wise, this would represent 4 different equations. And in principle, this should represent 4 different equations as well, but we put it all together with one solid expression, and eventually, when you move to comp form, you'll break it down. But this is ultimately what we're after, which I think jives with what we were working with in the earlier part when I said we want to show, see if I can find it, maybe not, maybe I didn't mention it before. So, sorry, but this is the final expression with in the true CFREE form. It does not have this little index anymore. That guy's gone. Okay, see you next time.